Hey guys. I was looking at the schedule about 5 minutes ago and saw RChain research group, and there was no name by it, and I was like, hey Greg, did Eitan or Joe show up to do this? He's like, I haven't seen him. So I was actually supposed to be at the testnet launch, but they're very able to do this without me. Not yet. So I came down here, and I can tell you something about the RChain research group, what the intent of it was. We've received a whole bunch of different proposals. I don't know whether I'll have the full list of those in time. I've asked for them, but we'll see if they show up. But yeah, Greg wanted to form a collaboration with universities, with people doing research in a bunch of different areas. So the letter they sent out said, we invite proposals for research programs on advanced development of the RChain platform. What features would you like to see in Venus? High-performance computing environments, blockchain deployment. Various universities have said, yeah, we're willing to run RChain nodes and try and optimize them, that sort of thing. Distributed consensus, particularly axiomatization. What does it mean to be a consensus protocol? You know, what axioms do one of those have to satisfy? Quantum consensus. Greg had an idea that you could use entanglement, since if you have a GHZ state, if any one measures a particle there, then everybody sees the same spin. But then you need a centralized supply of states, unless you're, anyway. Once you've got axiomatization of consensus, then you can see if it has models in Hilbert space. Economically secured leaderless protocols. Logic as a distributive law, that's what he and I have been working on. Related topics in type theory, category theory, semantics, concurrency theory. Interaction between blockchain and AI, the focus on compositional approaches to AI. I know that one of the proposals was looking at word2vec. Has anybody seen semantic vector spaces? Looked at that at all? Yeah. Okay, yeah. So the idea of word2vec is that a word gets its meaning by how it's used in context. So you start with a matrix whose rows are all of the words in your vocabulary, and whose columns are all of the forward contexts. So if you have a 30,000 word vocabulary, you have a 243 trillion context thing that you have to do there. And so then you'll end up with a very sparse matrix. For every word, you put a 1 in each column that identifies a context in which it has appeared. So you have this enormous, extremely sparse matrix, and then you will factor it into two matrices where the inner dimension is about 300. So much, much, much smaller than any of the other dimensions. And the best factorization gives you a lot of semantic meaning there. And so then you use the left-hand side that maps vectors, individual words to rows that are about 300 dimensions long, 300 elements long. And then you can do things like, if you take the vector corresponding to the word queen, and you subtract the vector corresponding to the word female, you get one very close to monarch, and then if you add male to it, you get one very close to king. And you can capture an enormous amount of semantic information this way. And one of the ideas was to do something similar to contexts in which variables were used and get some kind of semantic type system. So that was a proposal that involved AI. I think it was the only one, actually, that involved AI, but I thought it was interesting. And then finally, distributed and decentralized energy solutions. So Greg is interested in routing energy around and tracking that using using the blockchain. My role is really an advisory one, saying here are the interesting problems that I particularly am running into, that we're running into in development, how to build a type system, that sort of stuff. We received lots and lots of proposals. I think there are about 20 of them that I'm personally aware of, and all of them have been accepted so far that came from academic researchers. Luke Ong is here to talk about one of his things next hour. Talk about his proposal, I think. And there were several granted from individual researchers not associated with a university, but who had proposed independent things. We did get a few proposals that were more like, please fund our startup, and we referred them to Reflective and Pythia, because they're the better funding arm for doing startup stuff. But for research projects, we funded several of those, yeah. So Pythia is one company that Ed and Navneet started. So the idea from RChain was that they wanted to fund development of applications that would run on the RChain platform. And so Pythia has 100 million ROC and has been selling it in order to invest in various startups, as well as promising ROC for use by the startup. They have an obligation to find 12 companies a year to invest in. And you can read on GitHub RChain legal docs. So the RChain organization legal docs repo has the contract there with Pythia that lays out all the agreement that is there. But generally it's a VC arm of RChain. Reflective is another one. Pythia is run by Lawrence Lerner, and Reflective, I think, is run by Greg Heiss. Okay. Right, so the individual grants are on the order of 25,000 to 1.5 million. I think that $10 million were set aside for the RChain Research Organization. Part of the reason that it's done is as a marketing effort, that you know, if RChain were successful and took off, then people would want to research it anyway. But Greg wanted to preemptively get these professors and their teams involved in order to get it more well known in the academic community, to get young researchers invested in it, and to get the best type theory we could out of the knowledge that exists. Yeah.
Are there plans for renewing that at all? And if not, then how much of that million have already been granted out?
I don't know the numbers. I was hoping that Joe and Eitan would be here because they were the ones who were actively involved in making those decisions. Several of the proposals were, you know, over the course of 5 years, funding a principal investigator and several grad students. They were on the order of hundreds of thousands of dollars apiece, and I know that somewhere around 10 of those, so I'm guessing a couple million has been used. But again, this is like a 5-year funding thing that has been done. One part of the funding that's kind of interesting is that they're trying to fund it all using cryptocurrency. So the cooperative has Ethereum, has Bitcoin, has ROCs. So they've been working deeply with the universities who, as a whole, are a very conservative bunch, who say, we want to be paid in our own currency, national currency, and have it all up front. We expected to be turned down for the particular way of funding these projects, but then, we're trying to find out who the contacts are at the university, have a local representative who's there at the university advocating for us, many of these sorts of things. So working out the details of how to fund these projects is something that has been taking up a bunch of time there at the research meetings. 5 years is about as far out as anyone has hoped to imagine in the RChain project. We could be, bigger than Ethereum, we could be defunct by then. So as far as what happens next, I can't answer that.
I think I saw that there will be another round of
Yeah, we will probably have rounds of applications. The original letter said that we wanted to get applications before August 1st. That was pushed back a few weeks, and we got some more proposals, but people are continually sending us proposals. I don't know what Greg's plan is for funding those, whether they're going to be considered and funded, just continuously, or whether we're going to have a second call from proposals. That's much more of a logistical thing than I'm involved with. I'm mostly involved with the actual research itself than the logistics of the research. That said, I can speak to some of the research ideas that I've been involved with, but I know many of you are researchers as well. I'd be happy to hear from you what your interests are, as far as your research interests are, and how we can talk about how you might be involved. My particular interest is in type theory. It's how Greg and I met. The idea is that Lambeck and Scott gave a categorical interpretation of the lambda calculus. So lambda calculus, was invented back in 1934 by Alonzo Church. He was a logician. He was trying to formalize what it meant to be a function. He had a notion of type, that there were different kinds of questions. In his case, it was a question of syntax, like pronouns and nouns and verbs and things. How do you characterize the different parts of a sentence? Because the whole 19th century research plan was on, or in early 20th century, was on building up these logical constructs, propositions, statements, sentences, and so on. And so he had invented this thing and went on to use it to disprove Hilbert's decision problem. The idea, so David Hilbert, 1928, was perhaps the most famous logician of his day, and he had this idea that any question you could ask that had a formal description, there may be some formal way of answering that there's some algorithm for solving it. And they knew of several systems that were already that way. So for example, Euclidean geometry, you have questions about points and lines and circles and which points lie on which lines and whether they intersect or not, and those sorts of things. And because you can map lines to linear equations and circles to quadratic equations, then, because you can solve the quadratic equation, the question of which points lie on which lines was answerable always. And Euler was able to prove at age 17 that you couldn't construct the 17-gon, and went on to construct I think 65537 gon or something like that, and decided, okay, I'm going to be a mathematician, because he understood that connection. The question of what theorems are true in Euclidean geometry, in that sense, is the logic is consistent and complete. But what that axiomatization lacks is a way of multiplying integers. You can't, well, is it multiplication or division? Anyway, it lacks one of the fundamental arithmetic abilities. You can certainly take the product by multiplying as a parallelogram. You know, you put a certain number of lines there and a certain number of lines there, and then chop them up and count them and construct it that way. The division aspect, though, I think.
Are you asking if you could divide the letters in Euclidean geometry?
No, there's a restriction of Euclidean geometry to a certain set of axioms, and that one is consistent and complete. But it does that by not embedding arithmetic, basically. That.
Are you talking about one of the fields you can get irrationals?
No, I'm talking about the fact that to do a Gödel numbering, you need to have arithmetic. And so in any theory that's powerful enough to embed arithmetic, then you can do a Gödel numbering, and then you can construct this self-referential thing that breaks completeness. So anyway, the decision problem, you know, Gödel proved that Hilbert was wrong about the completeness aspect. Church proved that he was wrong about the decision problem, that there is no way to decide all logical questions. And Turing, unaware of his work, invented the Turing machine, found out about Church, then went on to show, hey, this computes the same set of functions. I think this is the only set of functions that you can, because we came at this from very different angles. And mine is much more mechanistic. And so when they were actually building machines to do computation, everybody followed Turing and forgot about Church for 30-odd years, a generation or so, until people started writing compilers, you know, having computers that were powerful enough to do compilation for you, and then they rediscovered Church. I've heard it said that the history of modern programming languages is the rediscovery of Church, right? Because you've got the original Lisp had dynamic scope instead of lexical scope. Anyway, early 1980s, we've got Lambeck and Scott. And they showed that if you take the types to be objects in a category, and you take equivalence classes of programs to be morphisms in a category, then the structure of that category was called Cartesian closed. And so they're saying programming languages are Cartesian closed categories, we can interpret them in each other. And that was widely regarded as a very fundamental advance in the understanding of programming languages and giving semantics to these programming languages. But you'll notice I said equivalence classes of programs. So in particular, what they would do is take a program and have one free variable in it. And you'd think of that free variable as corresponding to the input. You could also think of it as a term context with a hole. And then composing programs is you take one of these contexts and shove it into the hole in the other one, and you get a new context with a single hole in it. So those are the morphisms. But then they modded out by beta reduction, which is the act of substituting. It's also the entire process of computation in the lambda calculus, that the only way you make forward progress is by means of beta reduction. And so they were completely ignoring the entire process of computation, which was a reasonable thing to do, because they wanted to say, what does this program mean as a function? What function is it computing? We don't care how it computes the function, we just want to know which one it is. But then when we start writing programs, we care very much how it's computed, right? We want to use merge sort instead of bubble sort, right? We care about the complexity of these things. And so as we start thinking about how to implement a function, these rewrites become important. So my research with my PhD was looking at a slight generalization of this thing called a Cartesian closed category to symmetric monoidal closed, which is weakening the idea of putting two things together in a pair and being able to take them apart again. That's Cartesianness, is that you have products. In a vector space, for instance, you can take two vector spaces and tensor them together. You can take a vector in either one and combine them, put them together. But you can't necessarily take any vector in the tensor product of the two spaces and pull them apart again. The tensor product, you know, if U has n dimensions and V has m dimensions, you product them together and you have n times m dimensions. And so then you can do the point-wise, each element here times the corresponding element there gives you an entry in the matrix below. But given an n by m matrix, you can't always pull it apart again and get two vectors that would multiply in that way to give you that matrix. So that's why you can't pull them apart again. Symmetric monoidal closed categories turn up all the time in things like quantum mechanics, where you've got two Hilbert spaces. You're putting together particles and letting them interact, and the fact that you can't pull them apart again is entanglement. You have it in systems where you've got graphs, and so the rows are your source vertex and the columns are your target vertex, and you're counting paths between them, that sort of thing. So we've got computer programs, we've got Feynman diagrams in quantum mechanics, we've got topological systems like a pair of pants. If you start at the waist, you go down and at the crotch it splits into two legs. And so the objects here are disjoint unions of circles, you know, one at the top, two at the bottom, and then these smooth surfaces between them. That's another example, because I can take a pant leg and curl it upward, and so if we had a direction around the waist, say clockwise around the cuff, you turn it upward, it becomes counterclockwise. And so there's this contravariance that goes in there that you also see, and that's effectively currying topologically, is curling the pant leg upward. So there's this nice relationship between all of these different approaches, the computer science, the physics, the topology, and the logic. But I was really dissatisfied that the whole process of computation was being modded out in the computer science case, but in physics, you know, what's happening over time is the Feynman diagram. So Greg and I started talking about how that would show up in computer science, and he recommended that I start learning pi calculus. Unlike lambda calculus, which is confluent, that is, if the program ever stops by some reduction strategy, you'll always get the same answer. In pi calculus, you can do things like have race conditions. Somebody can win the race, someone else can win the race, and the effects of that are very different, right? You have ordering constraints, where you should really open the window before you stick your head out. Right? Socks usually go on before shoes. These are not commutative operations, and it really matters which one happens first. So we started looking into that, and over the past 10 years, we've been thinking about how to model that well. At the moment, we've gotten to something called the graph-enriched finite products category, looking at enrichments of Levier theories, which correspond to finitary monads, a whole bunch of higher category theory involved in modeling exactly how reductions occur in what order. And then Greg had this idea of deriving a logic from the term calculus and the ideas of the idea of a collection. So usually we would think of the set of things that matches a predicate. That's in Topos theory, where there's this isomorphism between predicates, things that say yes or no as they're looking over a set, and subsets. So a map from X to 2 is the same as a subset of X. In general, that doesn't hold, and so then you have a notion of a filter that can become more like a bandwidth filter, right? Rather than just saying yes or no, we can amplify the signal or shrink the signal. And a bandwidth filter is different than merely a subset of the thing. So we're playing with these ideas, trying to work out if we're given a description of, if we're given a predicate, some statement in a language that includes collections, then what is the interpretation of that formula? What is the set or list or tree or collection of terms that satisfies that? And trying to do all that using higher category theory. So that's what he and I have been involved with for quite a while. It's how we got to know each other. But we'd also like to know what you guys are thinking about and how you can, how we can work together to get everyone involved in making RChain a better thing. Anyone want to volunteer what they're looking at? Sure.
I have a question, if that's okay.
Yeah.
Fascinating talk. Thank you very much. So enjoying it so far. And a little bit off topic, but so just want to push this off. That's great. But can you talk a little bit about the virtual machine? So, you know, we've seen with the Theorem that the virtual machine has this serious problem in terms of how basically things are not deterministic or all the problems managing memory, whereas like virtual machine Cardano is built on a register-based approach that I think makes it easier to prove that things run according as they're expected. Can you talk about the virtual machine that RChain developed?
So RChain doesn't use a virtual machine in the same sense that EVM does. The semantics, the formal semantics we're giving is for the high-level language Rolang. Any implementation of that will necessarily be a valid implementation. Greg, when he started, had the idea that we would implement the entire platform in Rolang. And he had a virtual machine in mind for that implementation. But we very quickly found out that this old 90s virtual machine that was written in very imperative style would not translate easily to Scala. Our directive was to do an idiomatic translation of that virtual machine to Scala so that we could apply formal methods to that and prove that it worked in the same way. Unfortunately, an idiomatic translation couldn't be done efficiently. And you know, we worked on it for a long time. Finally, were able to give the precise place where it wouldn't work, and then gave it to Greg and said, if you know how to solve this problem, we'd love to hear it. And then he came back and said, yeah, that just can't be done efficiently. So we abandoned the Rosette virtual machine. In the meantime, to make sure that we could meet our deadlines, Kyle Butt started working on a Rosette interpreter. And so that is what we have deployed and what the test network runs on. Mateusz Gorski is working on the cost framework for the interpreter. So giving costs to all the different things that the interpreter does and accounting for those. That unfortunately makes it somewhat harder to reason about exactly what the costs are going to be. For Venus, we intend to revisit the virtual machine question. We'd like it to run directly on the metal. So we're going to hire a compiler team as well as a type theory team. So there are 10 development positions available if you want to work in type theory or compilers on a new language. Come talk to us. But for Mercury, all of the cost accounting is going to be done through the interpreter. Does that answer your question? Okay. Any other questions? Anything you'd like me to go into more depth about? Yeah.
Sorry, I'm supposed to talk about this. Maybe you want to talk
So then that becomes a nature of the question you are asking. I think that's the thing is, does there exist a number that is the encoding of a proof about lines and circles intersecting, right? That's a different question than do these lines and circles intersect, right? And so I think it's a question about what language you're allowed to use when asking your question that lets it be consistent and complete.
So I think at that point you wanted to refer to the Galois incompleteness theorem, which says, if I understand it correctly, that if a theory is to be both complete and consistent, it must not embed Peano's arithmetic.
Yes. Yeah, and so he was saying, but I think I can embed Peano's arithmetic because I can pick a line, and that'll be my real number line, and I can pick a distance, and that'll be my unit, and then I can count, and so I have all integers because I can go in both directions. And once I have integers, can I multiply? Yeah, I just take another line through it, count off that way, and then scribe them out. I've got a parallelogram. I can count the squares and do that many lines outward, so I've got multiplication. I think I can do division because I take this thing and chop it off, and then I see what's left over. So I can do rational arithmetic that way. Where does it fail? And so I think the way it fails is that what kind of question are you asking about the Euclidean geometry? And so does there exist such and such a thing is a different question than do these particular lines and circles intersect? Can you construct this particular length? And I think that's where the consistent and completeness comes in. But again, this is just all from memory, and I highly encourage you to go read the wiki pages, right? Any other questions? Yeah.
This is sort of flipping back to the more, with the Rosetta computer and the cost accounting operations, will there on RChain be something analogous to a block limit in terms of the maximum cost?
No, so the way it's going to work is that when you do a deployment, there are three parts. There's the code that you want to deploy, and then there are two wallets, one for each of the dimensions of phlogiston. And the wallets have to match a particular known format so that we know we're going to get money out of it at the end when we execute it. So we know we can just actually look into the code and see what the balance is. We don't even have to execute it. We just have to verify the signature on that, and then we can extract the money. So given these two wallets of known formats and the code, we acquire a bunch of locks that are necessary to prevent others from overwriting the data we'll be working with. We reduce the term, and at the end of it, we put the remainder on the chain. The process of reading the initial portion costs money, so that's going to come out of the computation wallet. If your thing is too big, you can't even read it all before your wallet runs out. If you are generating a whole bunch of data, writing that data to the chain costs money. You're going to run out of money before it gets onto the chain. Once the data is produced and the program is done running, then it starts charging the rent wallet. And so you'll have paid for a certain block height that you reach or a certain time, and once a block appears with a timestamp after that, then they're free to remove the term from the block. So that's the model of putting data on chain. So if I understood your concern was how do we prevent, whether there was a block limit on the gas. There's no limit on the block size of these deployments, but the gas limit is given by the size of, or the balance of the wallet that is provided at deployment in each of these deployments. So when another machine is receiving a block, it'll receive it in chunks, but it can look at the balance and start processing it, and when the balance is used up, it can just say, okay, you used up all your funds. There's this, you never get a situation where you have to do this enormous computation before you can claim the money, and it never finishes. So that's how you avoid the block limit issue, the gas limit issue in blocks, yeah. Yes?
I would encourage the whole, since we're all here together, like, to see what could emerge from this.
Yeah, sure. I don't need to be standing up here. I just figured that somebody should say something at this, you know. Yeah, I'd like to know who you guys are and what your interests are in being here. You want to go first?
So I guess my name's Christian. I sort of interested in various things like, say, philosophy of logic, philosophy of
Sorry, what logic?
philosophy of logic,
Okay.
philosophy of mind, but also, you know, sort of studying like proof theory and linear logic and other things, and sort of got sort of into this whole weird blockchain business stuff. And so, I mean, I'm very much interested in, say, like, sort of project of like artificially constructing languages for, you know, problems of economy. You know, there seems to be lots of things like with respect to, say, economic complexity, computational complexity, and some similarities between these things. Though, you know, a bit immature. But I also, writing in Berlin, I'm working on a project. Essentially, it's an economic grammar for building modular organizations and having modular forms do this. And Berlin was the only thing that is like available now that could, you know, serve that purpose. And so, and what else I should say?
Why is Redline the only thing currently available to serve that purpose?
So, a couple of reasons. I mean, one is like, it has, you know, nice properties that got me interested in interactive logic, like resource sensitivity, and, you know, like the Collins rule, it's very much like properties like cut elimination, models, interactions, rewrites are essentially interactions used to model economic structures. I mean, there's not really anything else that allows you that fine-grained control of information flow and how information flow is able to propagate through the system. The really interesting thing is that, you know, if you look at, you know, things like program execution, cut elimination, Collins rule as interaction, as information flows, as steps to these information flows. That is what gets written on the chain with the information flow.
So just a point about his COM rule there. He mentioned linear logic, and the idea of linear logic is that you are reasoning about resources. So the old aphorism that you can't have your cake and eat it too is the fact that there's only one cake. You can't set it aside and keep it and then eat the same cake. Whereas in classical logic, I can have a proposition A and derive from A that A and A is true. That doesn't hold in linear logic. I can't duplicate my keyboard or my hard drive, even though I can duplicate data. And so with the COM event he was talking about there, if you want to have a reduction in Rolang on the blockchain, you have to consume some phlogiston. There is a resource, phlogiston, that gets consumed as part of that rewrite. And so you can use linear logic to reason about resources that are available and what is produced at the end. You also can reason about things like I am sending one message on this channel. And if I have 10 processes listening on the channel, only one of them is going to get it. There's a race. So it's reasoning about messages as resources, contracts as resources, and what message flows are available.
Yeah, the interaction part I think is really key as well. Like I mean, that's why like it's like game semantics,
Mhm.
lytics, and interactions really became something.
Great. So if you're interested in any of that stuff, please talk to him afterward.
When you're able to put these interactions on the blockchain, it's complex and non-complex. That's I think
Yeah, to be able to do this between mutually suspicious parties. Yeah. Anyone else want to say what they're working on? Derek just walked in. He's the guy who's been doing all of our operational semantics for Rolang. He's producing a file in K-framework, which is a framework for doing reasoning about operational semantics produced by University of Illinois. Is that right? Yep. Yeah. Grigory Rosu is the principal investigator on that. Part of verifying the implementation will be showing that the Scala implementation matches the K-framework implementation. Whenever you're doing formal verification, you have to have a spec and you have to have your implementation, and then you compare the two, right? So doing two independent, computing this answer, quote unquote, the implementation of the thing in two different ways and then comparing them at the end is what we mean by formal verification. So this is a very important piece, and before mainnet launch, there will be a document that lays out all of the transitions explicitly. And then Martin from DAP-Hub, I don't see him here right now. Okay, yeah, I know he's here, I just didn't see him in this room. Remind me Martin's last name? Okay, Martin Lundfall. His proposal to the RChain cooperative was to take a K-framework operational semantics and derive from it a structural behavioral type system in using the ladle algorithm that Greg and I have been working on. So we will probably do the structural behavioral type system by hand for the structural part for Mercury and then the behavioral part for Venus, just so we don't have to wait for Martin. But it ought to be the case that any language you can express using K-framework, and they've done LLVM and JavaScript and EVM and all these things, you should just be able to push a button after saying, yes, I want to use sets for my collections, for instance, and it will derive a type system that you can then use for compiling or type checking contracts written in that language. Yeah.
How do you plan to compare the case specification of programs with the Scala implementation? Like, do you want to define the...
Well, we'll necessarily have to start with a Scala K-framework implementation, and then I think K itself provides tools for comparing two things and making sure that they are bisimilar.
Yeah, I think that's finished, but it has started at least.
Right, so we're certainly not going to have formal verification done before Mercury. And I think that the time frame for Venus is too short to have formal verification of Venus done at the time of release of Venus. But Mercury will continue as a shard of the Venus platform, and so we will end up verifying more and more of it. Yep.
After that, so DAP-Hub has been doing some really good work along those lines, and we will talk quite a bit more about that during the formal verification panel.
Great, so in case you didn't hear, there's a formal verification panel where they're going to address that question of how they're going to formally verify the implementation as well as how you can formally verify contracts later. Nobody else is asking questions, so.
Substrate independent semantics of maker that then checks the maker. So what I'm wondering is, like, does it make sense to then, if you have, like, say, you know, like a library or system built on top of Rowan, but say you've sort of abstracted the structure in a substrate independent way, you specify this in K, and then verify that these contracts obey these properties, given the work that you and Mark and so forth.
That seems to be a question about how you go about verifying contracts that you've written. For Mercury, we're going to be providing a spatial or structural type system. And that structural type system is pretty powerful. Most existing structural type systems are fairly weak. They only talk about the shape of data, right? So, you know, in TypeScript, you've got, say, an employee record, and it's got a name and an age, and the name is a string, and the age is a number, right? The way you write it is the same as you would write a specific record, but instead of the literal value for the name and the age, you put in a type identifier that represents a collection called string, that's the collection of all strings, and number, which is the collection of all numbers. And that's what makes it a structural type system, that it's using the structure of the term in order to describe a type. But in Rolang, you are describing the shape of programs. So you can say, I want to accept any program that includes a send on this name and a receive on that name. That is something you can express using the structural type system. So that itself becomes enormously powerful, that given some fixed points, you can describe, you know, this is, whatever process you send me has to be live in this certain way. It's got to satisfy this recursive structure on the program itself. That said, the behavioral type system is going to be even more powerful, because then you'll be able to talk about rewrites. And you'll say, I want a program that within 3 steps gets to sending a message on X. So I can bound the time that it will take to produce a message on X, something like that. Right. And so our hope is that your constraints will be easily expressible in this structural behavioral type system, and then will be type checked directly by the code running by the type checker that you would run on your code before deploying it, so that you wouldn't have to involve K-framework. That said, I think Derek could speak to it. I wouldn't be surprised if you could also do it by encoding what you want in K and then verifying that your implementation in Rolang matches it.
It might make sense. Cognitive resources to think about this yet. But that might make sense to do a substrate implementation and then check that the Rolang implementation obeys these properties, where you would have a K-framework specification for Rolang, a K-framework.
Sure, so the way you would approach it in K-framework is you verify that the initial state has the property you want, and that every possible rewrite out of that state preserves the property you're looking for, and then you're guaranteed that your program has that invariant.
Yeah, and often, like a contract can be written
Any other questions or comments? Yeah.
Yeah, I'm worried that my question was too easy for all the people here, but great conversation. Can you describe what is getting developed in Scala and what's getting developed in Rolang?
Sure. So anything that is off-chain, pretty much, is being developed in Scala. Had history been different, had we chosen a different VM, had there been an existing VM with a concurrency model that we wanted, perhaps we could have implemented Rolang very quickly and then developed the rest of the system in Rolang. The way things played out, however, Rolang, the interpreter, didn't even show up until, what, June or July of this year? So we didn't have time to write the entire rest of the platform in those few months. So we just decided we're going to implement it in Scala and expose the bare minimum necessary to Rolang to call out to Rolang. The registry itself uses the tuple space, and interacts by putting new Rolang continuations into the tuple space, but most of the logic itself is written in Scala. The tuple space is implemented in Scala, whereas Greg's initial design had it implemented in RBL, which was the Rosette-based language for the virtual machine. It simply became more efficient to use our Scala developers to write Scala, a language that they knew well, that had excellent support, had excellent tooling to develop the platform, and then grow the language itself to the point where you could start to think about doing some of these things in Rolang itself. So it's likely that much more of the system will be built in Rolang directly for Venus, rather than in Scala. Sure.
With Ladle, like, just trying to understand more precisely, but like if you would, for example, say that you use trees as your collection, what kind of time system would you get out?
It would necessarily be linear. So for instance, in a tree, you can have the same item appearing multiple times on different leaves, right? So because you're keeping count of how many there are, the term calculus itself would need to be linear. An example of this is the SKI combinator basis for combinatory logic. K is a combinator that takes in two inputs and throws away the second one. So if in the structural formula you had K of X and top, where top is some collection of all terms, say, the interpretation of that formula would be, let me use list just for simplicity. It has the same features, right? It's trees modulo associativity. It would be this list of all terms of the form kx something, right? If you then reduced pointwise, you would get x, 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 x infinitely many times. However, if you took your formula and then rewrote it as a formula, kx of top is x, then x itself is a one-element list. And those two don't match. And so this is a constraint on the distributive law saying, does your type system, does your term calculus distribute coherently over your collection calculus? So the left-hand side of the interpretation functor can be split up into three different natural transformations. There's the multiplication from the monad, there's the unit from the monad, and then there's the distributive law natural transformation. You get the formula language by taking your term calculus and adding it to the collection calculus. When you take the coproduct of monads, the functors that result, let me call the term calculus T and the collection calculus C. If I add them as monads, then resulting functors look like identity or T or C or TT or TC or CT or CC. It's any string of T's and C's. So you get essentially all binary strings interpreted as functors this way. And using the joins, we can collapse all strings that repeat down to one, collapse all those down to one. We can introduce a C at the beginning using the unit. And so then we get it collapsed down to one that's alternating CT, 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 and so on. We can introduce a T at the end using the unit. So we're guaranteed to get it into a form CT, CT, CT. And then the distributive law lets us move collections past terms. So we can collect all the C's on the left-hand side and all the T's on the right-hand side and then collapse all those down and get a collection of terms as the meaning of a particular formula. So we're adding them on this side. We've got just the composition of them on the other side, and this formula is interpreted as this meaning. But that ability to swap the two comes down to whether there's this coherence between the term calculus you're using and the collection calculus you're using. So in the case of lists, SKI doesn't work, but BCI for linear lambda calculus would. And you know, if you had a combinator expression of Rowlang, Yoshida worked out a combinator-based expression of pi calculus, and there's a similar one you can do for Rowlang. It's conceivable that a fragment of Rowlang that's linear in this way could work with trees. But our expectation is that if we have, say, sets of lists of composable rewrites, then we'd get quantile semantics for linear logic. And that's one of the goals, is to be able to reproduce various of these logics that we already know exist. Yeah. Any other questions? Yeah. No, it's you again.
If we don't mind, we talk about consensus algorithm as far as proof of stake goes. I understand like you're coding up Casper right now. Is that the case?
Casper is already coded up. Vlad Zamfir is going to give a whole presentation on Casper, if you want to go attend that later. We're at 12:09, so we're probably late for the next session. I heard somebody else clapping, so they were a little late too, but talk to you later.